Hello dear students, so let us start with the third unit of your 102 paper, so which basically deals with number theory. So we shall follow this book by David M. Burton, that is Elementary Number Theory. In number theory we will study the properties of integers, 0, plus minus 1, plus minus 2, as you know. So there are divisibility properties, division algorithm, GCD, LCM. Okay, many of these you have studied in school, but not in that much detail. Then about prime numbers, the properties of prime numbers, some theorems associated with that, and you will learn about congruences, okay, and how to do problems related to congruences. Okay, so we will start number theory with an important principle, that is the well ordering principle. So it's something like God of number theory. So it's a principle that we will assume without any proof. Okay, what does it say? It says that every non-empty set of non-negative integers, okay, non-negative integers has a list element, okay, or list member. So let me state it mathematically, that is given S is a non-empty set of non-negative integers, right. It contains, so there exists some list element, say n belongs to S, such that n is less than or equal to x for all x inside S. Okay, every element of S is greater than or equal to n. So that is n is the list element. Okay, so suppose you are given some set, something like 500, 123, so 2. Okay, so what is the least element here? The least element is 2. Okay, so the well ordering principle says, so for finite set it's obvious, you take the minimum element. Okay, and well ordering principle says that not only finite set, if you are given infinite set of non-negative integers also, you will have some list member. Okay, so that property is called the well ordering principle. So we will use this property to prove certain important results of number theory. Okay, so one of the important results is the division algorithm, which you have done in school level also. All of you have done this, but not in much detail. You have done it in this form. Okay, say dividend equal to divisor into quotient plus remainder. Okay, right, you have done it in this form. I hope everyone remembers. So once you do the division, say 153, you divide it by say 5, so it's say 5 is 15, and then 3 comes here, so it's not divisible. Okay, so 153 can be written as 5 into 30 plus 3. Okay, so this is the dividend, this is the divisor, this is the quotient, this is the remainder. So remainder has to be something which is strictly less than the divisor. Okay, so it cannot be something like say 127, if you divide it by say 3, 3 4 is 12. So we will not say that 7 is the remainder. Okay, because we can reduce it further. Okay, how to reduce it? We can reduce it something like 3 to the 6 and then 1. So we can write 127 as 3 into 42 plus 1. Okay. Okay, so this is, in this form we write it as divisor into quotient plus remainder. Of course, this is also true. 127 can be written as this 40 into 3 plus 7. Okay, this is also correct. This is the correct way of writing. Okay, but it is not the quotient and remainder form. Okay, we will not say that 7 is the remainder when it is divided. Okay, when we mean remainder, the remainder has to be less than the divisor. Okay, so we will learn why this restriction is given. Because under this restriction, this expression comes out to be unique. If we give this expression restriction that the remainder has to be strictly less than the divisor and it has to be non-negative. Okay, under that restriction, there is only one way of writing this in the form of divisor into quotient plus remainder. Okay, so for the uniqueness, this restriction is important. Okay? Otherwise, the same thing you can write it in several forms, right? You can write it something like 40 into 2 plus 40 into 2 is 80, 80 plus 47. 80 plus 47 is also 127. Okay, that is also one way of writing. You can also write it something like 40 into, oh sorry, I wanted to write it with 3. Okay, no problem. I can write it with something else. Say 40 into 5 minus 40 into 5 is 200. 200 minus how much should I write here? 200 minus something has to be equal to 127. So 200 minus 30 is, sorry, 200 minus 70 is 130. So minus 73. Okay, right? Am I correct? 200 minus 70 is 130. 130 minus 3 is 127. Okay, so I am poor at calculations. So this is basically the motivation behind studying the division algorithm. Okay, so let us state it properly. Division algorithm. What does it say? Let me state it directly from the text, whatever is written. If you are given two integers, so given integers a and b, given integers a and b with b non-zero, okay, b is not equal to 0, there exist, so this is the symbol for there exist unique integers q and r such that a is equal to b into q plus r, where there is some restriction 0 less than or equal to r strictly less than modulus of b. Okay, modulus of b, right? Given integers a and b with b not equal to 0, there exist unique integers q and r such that a equal to bq plus r, where 0 is less than or equal to r strictly less than mod b. Okay, so let us try to prove this. Okay, so we start with the set. Let S equal to this set. So what we do is you take this BQ to the other side and consider a collection of integers of this type. The set AS equal to A minus B into say some X. So here A and B are given to us. So we will vary the number X here. Okay. A minus Bx such that X belongs to integers. Okay, so X is an integer and A minus Bx is, so I am taking non-negative integers. Okay, collection of non-negative integers which are of the type A minus Bx. Okay. So yeah, so in the earlier thing in this statement, yeah, we had mentioned every non-empty set, it has to be a non-empty set. So we need to first show that S is a non-empty set. Okay, so can we find some element inside the set X? Okay, So here b is given to be any integer and b is non-zero. Okay, so b might be positive as well as negative. Okay, so first let us suppose that b is positive. Okay, then things will be a little bit easier. Okay, we suppose b is greater than 0. Okay, we suppose that b is greater than 0. So this set, let us try to find out one element inside this set. Can we find out such an element for which this quantity a minus bx is always positive, non-negative. Okay, so it may happen that a is negative also. There is no restriction on a. Okay, for a there is no restriction. So we need to choose the x in such a way that it is a minus bx becomes non-negative. Okay, so one thing that we can observe is this modulus. You have studied about modulus. Modulus of a is always greater than or equal to a. Okay, modulus of a, this is always greater than or equal to a, right? And since your b is a integer, right, so b into modulus of a, b is already greater than 0, so modulus of a into b, that is also greater than 0, right? Also b is given to be an integer, so not only b is greater than 0, b is actually, since it is an integer, so the next value after 0 is 1, so b is actually greater than or equal to 1. So if we multiply b both sides, if we multiply this inequality both sides by mod a, so its mod a into b is greater than or equal to mod a. Okay, so if we have mod a into b, then numerically, or the positive value of this is always greater than mod a. Okay, so here we have something like a minus bx. So if we take x equal to mod a, so this is going to be negative, a minus b into mod a. B into mod a is already greater than this a. Okay, so that's going to be negative in that case. But if we take x equal to minus mod a, in that case you see this becomes positive, a minus b into minus mod a. Okay, so this will become a plus b into mod a, but b into mod a is numerically it's larger than modulus of a. So modulus of a is already greater than or equal to mod a. Modulus of a is already greater than or equal to a. So numerically this value is larger. So even though this a may be negative, when we add them, this sum will be positive. Okay, this plus a will be positive. Okay, or say non-negative. So this is what we will take. So suppose we suppose that b is greater than 0. So b is greater than 0 means, so b is greater than or equal to 1. So b is greater than or equal to 1, and thus mod a into b, this will be greater than or equal to mod a, right? So taking x equal to minus of mod a, we have a minus bx, which is equal to a minus b into minus mod a, right? This is equal to a plus b into mod a. This is always greater than or equal to 0. So therefore a minus b into minus mod a, okay, this is an element inside S. Okay, right. So we have got that S is a non-empty set. So S is non-empty. So what can we say? We can say that S is a non-empty. So S is a non-empty set of non-negative integers. Okay, by definition we have taken only non-negative integers. Non-negative integers. Okay. So S is a non-empty set of non-negative integers, right? So by well ordering principle, so here we see the application of the well ordering principle. So by well ordering principle, S has the list element, okay, the list element R, okay, say. So suppose that we have named that list element as R, okay. So therefore we will write this R as R equal to A minus B into Q for some Q inside the set of integers, okay, because the definition of S says that S is what? The set S was the collection of all A minus Bx such that X is an integer and A minus Bx is greater than or equal to 0, right. So we have gotten a list element R which is inside S. So R will be of this type, A minus B into something. So that something we have named it as Q, okay. So this means A is exactly equal to BQ plus R. So the existence part we have shown, okay. So there exist integers Q and R which satisfies A equal to BQ plus R, okay. Next I have to show the uniqueness part, okay, that R lies between 0 and R is strictly less than modulus of B, okay, right. Okay. So for that we have to first see if R can be greater than B or not, okay. So if R is greater than B, then what happens? If R is greater than B, okay, then so let us consider this this one, A minus Q plus 1 into B, this integer. So this is what? A minus QB minus B. So what is that? If R is greater than or equal to B, okay. So A minus Q plus 1 into B is A minus QB minus B. So A minus QB is already or A minus BQ is already R. So this is R minus B. So R is greater than or equal to B. So R minus B is greater than or equal to 0, right. So then what is the problem? The problem is that A minus Q plus 1 into B is an integer which is non-negative. So and it is of the type A minus Bx. So this integer belongs to S, okay. A minus Q plus 1 into B, this is an integer which belongs to S, okay. Then what is the trouble? The trouble is, see, this integer is exactly equal to R minus B, and whether it is less than B or greater than B, R minus B. R is a integer, right. R is a of course positive non-negative integer, and B is a positive integer, okay. So R minus B is always R minus B, this is always less than R, okay, because if you take the difference R minus B, what is that? This difference is R cancels, so this difference is B which is greater than 0. So R is greater than R minus B, okay, right. So that means what? We have got an element inside S which is strictly less than R, but this cannot happen. Why? Because R is what? R is the least element of S, smallest element, okay. R is the smallest element of S. By Eulerian principle we get the smallest element of S is R. So nothing smaller can than R can be there, okay. So so that creates the problem. So R, if R is greater than or equal to B, we will have a contradictory thing. That means the R, the smallest element that we are talking of, has to be less than B. If it is greater than or equal to B, it cannot be the smallest element, okay, right. There are many R's which satisfy A equal to R equal to A minus BQ. Out of them, the smallest we have chosen by Eulerian principle, okay, right. So this is what we will write. Thus A minus Q plus 1 into B, sorry, A minus Q plus 1 into B to B, this belongs to S, okay, but this is not possible. This is not possible as as what happens, a minus q plus 1 into b is actually r minus b, which is strictly less than r, but this is not possible as this is strictly less than r, the least element, which is the least element. So it contradicts, it is contrary to the fact that R is the least element of S. Okay, R is the least element of S. So therefore, R cannot be greater than or equal to B. So R has to be strictly less than B. Okay, and already R is greater than or equal to 0. Also, because R is an element of S, R is greater than or equal to 0. So thus 0 less than or equal to R, strictly less than B. Okay, so this condition is already there. Okay. Now we will show the uniqueness part. Okay, so the R that we have chosen by validating principle is unique. Okay, and not only R, the Q is also unique. Okay. So the uniqueness part, uniqueness of Q and R. Okay, so suppose there exists some other Q dash and R dash. Okay, there exists Q dash and R dash such that A equal to B Q dash plus R dash, where 0 less than or equal to R dash less than B. Okay, then what you have, BQ plus R, A is already BQ plus R, so this has to be equal to BQ dash plus R dash. Okay, so this implies B into Q minus Q dash, this is equal to R dash minus R, right? So from here, if you take the modulus, so it's mod B into mod of Q minus Q dash is equal to mod of R dash minus R, but mod B is B because B is positive, we have supposed. So mod of Q minus Q dash is equal to mod of R dash minus R. Okay, now R dash and R, they lie between 0 and B, so mod of R dash minus R, it cannot be more than B. Okay, why? You see, 0 less than or equal to R less than B, this is already there. 0 less than or equal to R dash less than B, this is also there. So if you multiply here by minus 1, you get something like minus B less than minus R less than or equal to 0, right? Minus R lies between minus B and 0. So if you add them, so it's minus B strictly less than R dash minus R less than B. Okay, so R dash minus R lies between minus B and B. So this quantity is always strictly less than B, right? So we'll write here, but mod of R dash minus R is strictly less than B, as this 0 less than or equal to R dash comma R less than B. Okay, both of them are less than B. So their difference, modulus of their difference cannot exceed B. Okay. So what we have, B into this quantity is less than B, right? Thus, so mod of R dash minus R is same as B into mod of Q dash minus Q, right? Or Q minus Q dash. What did I write? It's the same thing. Q dash minus Q or Q minus Q dash. Let me write it as Q minus Q dash only. Okay, Q minus Q dash. This is strictly less than B. Now B was given to be positive, so we can divide both sides by B. So from there we can get mod of Q minus Q dash, and this is strictly less than 1. Okay. So but yeah, so that is this mod of Q minus Q dash is always greater than or equal to 0. Okay, it's the modulus. So 0 less than or equal to mod of Q minus Q dash, strictly less than 1. Okay, but what is Q minus Q dash? Q minus Q dash is an integer. Okay, so an integer, or in particular mod of Q minus Q dash, that is also an integer. So it's an integer lying between 0 and 1, and it is not equal to 1. So what is the only possibility? So therefore the only possibility is mod of q minus q dash is actually equal to 0. So that means q is equal to q dash. Okay. So once we have proved q is equal to q dash, we can easily show that r is equal to r dash. Thus b into q minus q dash equal to r dash minus r. This was already there, but q is already q dash, so b into 0 is equal to r dash minus r. So this implies r dash is same as r. Okay, so therefore q and r are unique. So there exist unique integers which satisfy this, right? So one part we have proved using or assuming that b is positive. If b is negative, what we can do is, if b is negative, b less than 0, then we can work with mod b. Mod b is greater than 0. Okay, so there exist. So just now we have shown. So there exist unique integers. Q and r such that a equal to mod b. So we are taking mod b as the divisor now. Okay, mod b into q plus r, where 0 less than or equal to r strictly less than mod b. So this can be written as what? But I want to write it in terms of b. So since b is less than 0, what is mod b? Mod b is same as minus b. So minus b into q plus r, 0 less than or equal to r less than mod b. Okay, since mod b is same as minus b, b is negative, so say mod of minus 2, what is that? It is minus of minus 2, so that is 2. Okay, like that. So mod of b, since b is negative, mod of b is same as minus b, so we have got a equal to b into minus q plus r. Okay, so in this case the quotient is minus q, 0 less than or equal to r less than mod b. Okay, thus given integers a, b with b not equal to 0, there exist unique integers q and r such that a equal to bq plus r, with the restriction that 0 less than or equal to r strictly less than modulus of b. Okay, so this is the proof of the division algorithm using the well ordering principle. Okay, so for example, if we have a equal to say 537, b equal to, suppose I am dividing it by say 11, so what will be your q and r? As per the division algorithm. Okay, so 537 can be written as, so you can do it mentally, that's, you have done it in school days also. So 11 into what? 11 into how much should I take? So 11 4 times if I take, it will be 44. 44 plus 9 is 3, so it's 97 here. So 11 8's 88. 88 plus 9 is 97, right? 88 plus 9. So it's 11 into 48 plus 9. Because this is the unique expression. You cannot find any other expression involving this remainder term strictly less than 11. Okay, that is not possible. Of course, you can find something more than 11 or less than 11. You can find something more than 11, maybe less than 0. That is possible, but you cannot find any other thing which lies between 0 and 11. Okay, 0 and 11. Say if I take 11 into 47, okay, then this will be 11 into 47 is what? 47. So this will be exactly, you can actually compute, this is 20. Okay, so this will be 517 plus 20 is 537. Okay, so if I take 11 into 46, so I don't have to compute, I will just keep on adding 11 here, it will be 31. Okay, like that. If I take 11 into 49, okay, so I have to subtract, because 111 I will get extra, right? 11 into 49 minus 1 plus 9, so this is 11 into 49 plus 9 minus 11, so that's minus 2. Okay, but these are not considered as the division algorithm expression. Okay, so the division algorithm expression is unique. right? 537 is exactly 11 into 48 plus 9. Okay. Say suppose I take A as 5 and B as minus 3, then what are the things? So we are dividing 5 by minus 3. So how much should I take? What should be the quotient and remainder? So if I take one time, it is what, minus 3. So 5 minus 3 is 8. So it's not correct. Say take minus 1 times, it is plus 3. 5 minus 3 is 2. So 5 can be written as minus 3 into minus 1 plus 2. Okay. So this is the unique expression. So Q is minus 1 here and R is 2 here. Okay. Similarly, if I take A equal to minus 5 and B equal to 3, in that case, what will be the quotient and remainder? A is minus 5 and B is 3. So how much should I take here? The remainder has to be positive. Okay, no, non-negative. It may be 0 also, no problem. Okay, so I have to take something, some number here, so that this becomes larger than numerically larger than 5. Okay, so after subtracting, numerically, yeah, larger than 5 and negative. Okay, so that after subtracting we get something positive here. So if I take minus 2, so 3 into minus 2 is minus 6, and minus 5 minus 6, so that is 1. So just check, minus 5 can be written as 3 into minus 2 plus 1. Okay, so see, the remainder is non-negative. Remainder should lie between 0, 1, 2. Okay. So if we divide a number by R, so what are the possible remainder? So if if we divide A by B, which is non-zero, then the only possible remainders, okay, then the only possible remainders are what, 0, 1, 2, 3, up to what? It can go up to mod B minus 1. Okay, these are the only possible remainders, right? Because the remainder has to lie between this 0 less than or equal to R strictly less than mod B. So it can go up to mod B minus 1. Okay, so that was the division algorithm. So in the next lecture we will do some problems which make use of the division algorithm, right?